All right, I think it's time. Welcome back to everybody. We do not have homework due for today, so I hope you have enjoyed your week off from the homeworks. We'll get back onto it next time. We've been talking about fair division procedures, and I had one little thing, something I mentioned at the very end last time. These procedures, that is the lone divider and the last diminisher, both, the point of these, the purpose of them is to make sure that everybody gets a fair piece, right? The lone divider is done for 3 people. The last diminisher you can do for any amount of people. They both ensure everybody gets a fair piece. What I mean by fair is value 1 over n in their opinion. If n is the number of people in the situation. So if there's 3 people, everybody should get at least value 1/3 in their own opinion. If there's 4 people, they should at least get value 1/4. All right? So that is called proportional. So they are the technical word for those. They are proportional. That means everybody gets their fair share. All right? But one thing that I mentioned at the end last time is, even though everybody's getting a fair share, it might be that somebody likes somebody else's piece better than the one that they got. And that's a different matter. So they are proportional, but they are not always envy-free. Right? And what that means, envy-free, means that at the end, nobody is envious of anybody else. That means nobody would prefer somebody else's piece rather than the one that they got. So envy-free, maybe it's easier to say what envy means. Envy means somebody prefers a different piece. I'll say a different person's piece more than their own. And this can be a problem in real life, especially if you're like trying to share things with kids. Even if a kid is getting their fair share, they're still going to be upset if they like somebody else's piece better. They'll say, no, Jimmy got a bigger one than me, and you can say, well, yeah, but your piece is still technically like 1/4 of the total or whatever. And they'll say, I don't care because I like that other one better, right? This is undesirable. Envy means somebody prefers a different person's piece more than their own. And these methods do not guarantee that there's no envy. And we saw at the end, at the example we did at the end last time, and actually many examples. If you look back at all the examples we've done, there are many times when once we get to the end, you can look back and realize that actually somebody would have rather had one of these other pieces. Anyway, so it's much harder to make a procedure to avoid envy. So making envy-free means there is no envy, right? Envy-free procedures is much more complicated. And for 3 people, there is one which was developed, I mean, as far as the history of math goes, fairly recently, like in the 1970s, I think. For 3 people, there's it's called unfortunately, it just has some people's name attached to it. The Selfridge and Conway, these are 2 different people. Selfridge and Conway procedure. And this is a method for dividing among 3 people, which guarantees everybody gets a fair share and also guarantees that the division is envy-free. All right, this is called the Selfridge-Conway procedure. And if you look on your big list of topics, this is the next one, is the lone divider, the last diminisher, and the Selfridge and Conway procedure. The point of this is that It still works for 3 people, but it guarantees that there's no envy at the end. And so this is sort of better than the other one for 3 people that we've talked about. I hope that this sounds interesting to you all. Unfortunately, I've been looking at my calendar lately, and I feel like we should be getting on with the material. I want to get on to the next section, so I have decided to skip the Selfridge-Conway procedure. I hope you don't mind. This is what it's for, though. It's an improvement on the other ones, which removes the issue of envy. So, if you have your checklist with you, I got my checklist right here. I would invite you to put a big old line through this one. I think I will just leave the numbering. You know, I like to have the numbers the same on the tests and on the list. So we're going to just have no number 19 ever, all right? And we'll skip down to number 20. So from the fair division, we just have the lone divider and the last diminishing. I hope no one is upset about that. I wanted to get to more of these topics about graph theory. All right, so we're not going to do the Selfridge-Conway. Sorry for all the Selfridge-Conway fans out there. I'm sure you can read up on it if you're interested. This is the envy-free procedure for 3 people. I thought it might be something that is interesting about this for, say, n people, n greater than 3. This is still a very important kind of unsolved problem in mathematics. There is not a very good method that is known to do envy-free division for more than 3 people. No good methods are known. For 3 people, you can do this Selfridge-Conway thing, but actually that is special for 3 people. It only works for 3 people, and it's very difficult to invent a similar method. So think about it if you like. If you come up with something, you may become famous in the world of mathematical fair division. I'll tell you sort of the state of the art here. So this is very recent in terms of like mathematical research. I don't know if you ever thought about like what's the ordinary people such as yourselves. What's like the newest math that you have ever learned? Like if you know calculus is fairly advanced, and I assume that not all of you, maybe some of you taking calculus. That calculus was invented in like the 1600s. Can you do any better than that? I don't know. Compared to like the mathematical knowledge that you have, these topics that actually we've been talking about in this class are far newer than, say, calculus. But anyway, in 2016, a procedure this is an envy-free procedure for n people was discovered or invented, however you want to say it, was invented. Unfortunately, it requires a lot of cuts. The idea is you cut the thing into like a million pieces and then assign these little bits to the different people. And so what the pieces are not like just like one piece of cake. It's like you're getting a million tiny little bits of the cake, which you can then, I suppose, glue back together or something like this. But anyway, this is ridiculous what I'm about to say. But this is like a published research article in 2016. A procedure for n people was invented. It requires this many steps in order to do this procedure. I'm not making this up. N to the power n 6 times. That's a ridiculous number. Like even if n was just say 4, 4 to the 4 to the 4 to the 4 to the 4. This is already like bigger than your calculator can handle or something. So this is like I would say there does exist a procedure that is known about, but you would never actually be able to do this in real life because it requires way too many steps. And so the question of like, can you invent a procedure that you could actually, practically speaking, do? Like even if you're using a computer, you wouldn't be able to evaluate something with that many steps. The question of an actual like workable method, that's why I said no good methods are known. This is still an unsolved problem. So get to work if you're interested in that sort of a thing. Very strange. There are still lots of people working on this problem. It continues to be an active area of research. And to be honest, I am not a researcher in this area. You know, I do my own math research, but it has nothing to do with this problem in particular. So I'm not an expert. Any thoughts about that? If you're trying to divide cakes with, you know, you and your 4 friends, the moral of the story is there isn't really a method where you can guarantee that everybody gets a fair piece, and also everybody thinks that their piece is the best, better than everybody else's. That is usually unobtainable using current mathematical knowledge. All right, this is all I want to say about fair division procedures. We are not going to talk in detail about the Selfridge-Conway procedure. It's not so hard, you know, we could have done it in a day or two, but I'd rather get on to something else. All right, the end of the fair division procedures. This is going to be the beginning of our last major sort of batch of topics for the semester. I want to talk about graph theory. Graph theory. Surely you all know, you know, from your youth, you have been talking about like mathematical functions and the graph of a function. That's not this. So graph theory is something completely different. Like the word graph in mathematics is used in 2 different ways. One is the graph of a function, which you're all familiar with, but that's not this. Graph theory is something different. So let's just get into it. Graphs, I'll tell you what a graph is. Graphs are things like this. Oh, sorry. They are sort of, you could think of them as a diagram involving dots and lines. All right, so this is a graph. It has dots and lines connecting the dots to one another. That's what a graph is. It is allowed to have a line sort of going from one dot back to itself. But anyway, that is a graph. There is a huge amount of mathematical research done about graphs, these things, because they are super important in the modern world. Like people use graphs all the time to do all kinds of stuff. I would say like in the history of mathematics, graphs are fairly recent. I mean, like people started taking graphs seriously like in the 1900s, so more recent than, say, calculus. I would say most of what you learn like in high school math is aimed to get you towards calculus, even though not everybody learns calculus, but like math that you learn in high school is typically all of the math which was invented in order to do physics. But graph theory is not helpful in physics. It is super helpful in all kinds of other things, though, in real life. So anyway, graphs are super important. We'll talk about lots of examples. But for now, let's just talk about what it is. This is a graph. The ingredients of a graph, the dots and the lines. So the dots, this is the terminology here. The dots are called vertices. This is the plural. Vertices, or the singular is vertex. So each little dot is a vertex. The plural of the word vertex is vertices. The dots are called vertices, and the lines are called edges. So this is always the terminology that I'm going to use to describe a graph. A graph is a collection of vertices and edges in some kind of arrangement. All right? And let's just talk about some very basic terminology about a graph. So basic terminology, terms. One thing that's super important about a graph is, here's a basic terminology that's not all that important, but a loop edge is, there's actually one looped edge in this graph here, and you can probably tell which one it is. It's an edge connecting one vertex back to itself. All right, this is not all that complicated. Something more interesting. each vertex has what we call a degree. So the degree of a vertex, sorry, that says degree of a vertex, is the number of edges touching it. That's called the degree. All right. So on my picture up there, maybe we could just write in the degree next to each vertex. For example, this vertex right here, what is its degree? It's just how many edges are going into this dot, and that is 2, right? So this vertex here has degree 2. I'll just write it right next to it. The one sort of on the bottom from there is also degree 2. There's 2 edges that touch that vertex. The one on the top, also degree 2. All right? It's because right here I see 2 different edges going into that one. What about this one? Here I see 3, right? 1, 2, 3. There are 3 edges there, so this one has degree 3. This has 2. This also has 2. And this one down here, this is a little strange, but this has 3. We count on a looped edge. We count those as 2 separate contributions to the degree. All right. So the degree is always just how many edges are coming into this vertex. If you're ever like a little concerned about how do we know exactly what the degree is, you could say like draw a little circle around here and then count kind of how many lines are going into that circle there. There's 3 of them. All right. Anyway, that's called the degree. The degree turns out to be super important, and we're gonna a lot of what people talk about in graph theory is based on things related to the degree. All right. Okay, something else that's important about a graph. A path in a graph is just some kind of sequence of vertices that are connected by edges where you can you imagine yourself sort of like walking around inside the graph along the edges. So a path in a graph is a sequence of vertices connected by edges from one to the next. So for example, if I have a graph like this, I'm just making up an example here, and I'm going to give names to these vertices. Let's call them A, B, C, D in the middle, and E down here. So in here, something like A, B, C, D is a path. You imagine what that means is like you're a little guy and you start at A and then you go to B and then C and then D. So that's a path, all right? You can imagine this as a little ant walking around along the edges, all right? But for something like A, B, E, A, this is not a path in that graph because you can't go A to B and then to E. You can't go from B to E along an edge, all right? So this is not a path. That's because there's no edge B to E, right? And so that does not count as a path. All right, very, very simple idea, I think. I'm not trying to say anything complicated here. This is just terminology and how we talk about things in a graph, all right? A sequence of vertices connected by edges. Okay, there's a special kind of path which comes up often, and we call it a circuit. A circuit means a path where you start and end at the same point. So it also represents sort of like a little guy walking around inside the graph, but that little guy begins and ends at the same point. So a circuit is a path beginning and ending at the same vertex. That's called a circuit. All right, so like in this example right here, something like A, B, C, E, A is a circuit. Right? Because you can actually go along edges around the graph like that and end up back where you started. All right. There are also sort of like stupider circuits. For example, A, B, A. That's also a circuit. Right? That would be, you start at A, you go up to B, and then just immediately come back to A. That's allowed. That's kind of a stupid circuit, but it is a circuit. You just have to go somewhere and come back to where you started. All right? These are the basic terms that we're going to use all the time about a graph. One other bit of terminology that I would like to spend maybe a few minutes discussing. This is also a very simple idea, so this is not a confusing idea at all. But I will say some graphs are connected. And this is a very intuitive idea. I think everybody will immediately know what I mean by connected. Actually, I've drawn two graphs so far today, and they are both connected. Something like, I'll just draw another one that's connected. About this. This is connected. That's connected. It means sort of like it's all just like one big connected thing. Versus what would not connected, we call disconnected, would be something like that. That is disconnected, all right? Because it's not just like all one connected thing. It's sort of disconnected. I hope everybody knows what I mean when I say connected or disconnected, all right? Actually, I would like to give a real definition for this. I thought maybe, I hope it's not too early for this, maybe we could have a little class discussion. We could put the desks in a circle. We don't have to do that. But can we have a real definition of connected? What I said before, I hope that everybody has the idea of what I'm talking about here. But what I said before was not a very satisfactory definition. I said something like, okay, this one here, this is connected because it all makes like one big connected thing. But of course, you're not supposed to use the word as part of its own definition. I said the word connected. Anybody got an idea? And I said disconnected. I said like it's like two separate disconnected things. But even so, I'm not really. This is not a very satisfactory definition for me to be using the word connected and disconnected. Anybody got any thoughts about this? Can we say in some kind of, it doesn't have to be super sophisticated, but at least don't use the word connected when you give the definition of connected. Yeah.
Each vertex has a degree greater than 1.
This is a good idea. Each vertex has a degree greater than 1. This is a good idea, but not quite true. Because, for example, I could just sort of add another guy on here. And now this one does have a degree 1, even though it's still connected. Yeah, that's a good idea, though. I would like to give this definition in terms of some of these words here, although I don't think the degree is not exactly the important thing here. And we got another idea? I think if you were trying to like explain this to your grandma, you would just say, yeah, connected just means like it's all one big thing. But that you gotta do a little better than that if you want a real mathematical definition. Any thoughts? Yeah?
Like there's no gaps between like
no gaps. Yeah. Between what I interrupted you by repeating your words.
I think I mean like between like like they're all like there's no gaps.
You almost said it. Yeah.
There's no gaps between like the vertices and the edges.
Yeah, something like that. There's no gaps. I like this idea. I think the idea is something like like over here, I might say like, well, isn't there kind of a gap like from this one to that one? Because it's like there isn't an edge right there. But this is not what you mean, right? Because from this one, you can still get to that one by going boom, boom, like that, right? Yeah. So it has something to do with like, from any one of the vertices, you can still get to all of the other ones. Like that's not true over here, right? You can't, for instance, like starting here, you can't get to there because there's a gap, like she said. Can anybody say this? Perhaps using one of the words that we already underlined. You have to say something about like connected means like you can always get to somewhere else, whereas disconnected means there's some places you can't get to from some starting point. Yeah?
There's a path between the
Yeah. This is actually about paths. So this is not an obvious definition, although it's a totally like natural concept. But the definition is not exactly obvious. But this is the definition. So I'm going to write this with a little diff. A graph is connected. What she said, there's always a path between any two vertices. So I'm going to say a graph is connected when any two vertices can be connected by a path. Maybe I shouldn't use the word connected again, but I'm using it in a different sense. I will just say any two vertices can be joined by a path. Right? And by joined, I mean you can start at one vertex and do a path and end at the other vertex. So I'm not saying any new undefined words this time. That's what connected means. All right? And then disconnected would be the opposite of that. I'll just write that. It's disconnected when there's two vertices with no path between them, right? This is a non-obvious definition, but it is an obvious idea. I think the concept of connected versus disconnected is totally obvious, but it's actually kind of tricky to come up with the real definition. But that's the way it goes sometimes in mathematics. All right, this is what connected means. Any thoughts about that? So actually the first item on your big list here is just paths, degrees, connectedness. This, in my opinion, is a very easy one on the big list. So I hope that everybody by now understands what paths, degrees, and connectedness means. Degrees are the number of edges touching each vertex, and connectedness is what we just talked about. All right, questions about that? You'll see something, some things on the homework. I think we can go right on to the next bit. Imagine a graph and answer questions. So I want to talk about what graphs are used for in real life. Graphs are used all the time in real life. They're very important in computer science, in all kinds of things in real life. Graphs tend not to be used in the natural sciences. So graphs are super important, I will say, in social sciences, not so much in the natural sciences. So like they don't use graph theory a lot in physics or chemistry. They do use it. It is more applicable in biology and much more applicable in just like sociology, analysis of social structures, things like that. Computer science is super important. Mostly super important in social sciences. I would say sort of human-made sciences or human-made, structures are often, I'm trying to write the word structures here. This is when you tend to see graph theory, as opposed to like the natural world of, say, physics and chemistry. Graph theory is not as applicable in those settings. But anyway, I would like to do several examples, which I call Imagine a Graph. I'm going to try and describe a scenario, and then we're going to try to invent a graph which represents the information in that scenario. And these scenarios will be very ordinary, kind of like real life situations. So here is an example. How about I have 6 kids. This is not a true story. And their ages are 3, 7, 12, 12. Those are the twins. 18 and 19. All right? So, let's imagine this is not a true story. I have 6 kids. In real life, I have 2 kids. And that's enough for me. These are the ages of the kids, all right? And let's say that, of course, when you have a lot of kids, they have sort of like natural sort of social groups. Let's say they are friends with one another if the difference in their ages is less than or equal to 5. All right? This is my scenario. I would like to represent this situation using a graph, and then maybe looking at the graph, what can we tell about this situation? So let's represent this using a graph, all right? Now, in this example, I have 6 kids, and those kids are each going to be a vertex in the graph. And then the edges will represent the various like friendships that I'm discussing here, all right? So we have kids, 6 kids related by friendships somehow, right? Like some kid is friends with some other kid, but some kids are not friends with other kids, and it has to do with the ages being less than or equal to 5. So there are 6 kids related to by friendships. Some of them are connected by friendships, and some of them are not. All right, so the kids here will be the vertices, and these relationships will be the edges. All right. So let's try and draw the graph. I've just so I don't scroll. These numbers are important. I'm going to bring them down here. There are 6 kids. Those are the ages. So I'm just going to make a graph. I mean, I don't know how the edges are going to work out, but I'll just draw 6 vertices, and I will label them by the edges. So they go. Maybe I'll put them like this: the 12, the other 12-year-old, the 18-year-old, and the 19-year-old. All right. So those are the various 6 kids. And now I'm going to draw in the edges according to the rule that I said before, which is they are friends if the difference in their ages is 5 or less. And so you just have to look at each of these vertices and decide which one should be connected. Like, for instance, should the 3 be connected with the 7? I say yes, because the difference between 7 and 3 is 4, and that is 5 or less. So the 3 and the 7 will be friends, so I'm going to put an edge there. What about the 3 and anybody else? I think actually there should be no edge from the 3 to any of the others, because all of the other ones are bigger age difference, right? 3 to 12 would be 9 years difference, so there should be no edge there, and it's even worse for the other ones. All right. What about the 7? Who should the edges from the 7 be? Can anyone say? Yeah? To each of the 12s, yes, and not to the 18 or the 19, because those are two big difference. So the 7 gets an edge to each of the 12s, all right, and not to the others. What about the 12? How about, say, the first 12 here? Are there any more edges that I should draw in here? To the other 12, yeah. And I think none other, right? The 12 should not be connected to 18, so like so. All right. How about this 12? I think for the same reason, this 12 doesn't get any more edges, right? They're only connected to the 12 and the 7. The 18 here, I think, does not connect to the 12. It should connect to the 19, and that's it. And I think actually those are all the connections that should exist in the graph, all right? So the graph is a way to analyze kind of like the social structure of what's likely to go on with my kids, all right? So by looking at the graph, what kind of information do you get from the graph? So we can see, first of all, I would note that it's disconnected, right? You can tell it's in two pieces. And what does that mean, like in real life, in this scenario? I would say what that means is when my kids are like hanging around, I would expect for them to naturally separate into two groups when they're like playing together or whatever. I would expect the 18 and the 19-year-old to sort of stick together, and then all of these other ones to stick together, right? Because that's what the structure of the graph suggests. So it's disconnected, and this means like IRL. In real life, the kids will naturally fall into kind of two social groups, right? And I can tell that just by looking at the graph. Now, if I didn't draw the graph, you might have been able to figure that out anyway, but looking at the graph is very clear, I think. The kids will naturally fall into two social groups. Another thing that I would say is, just by looking at the graph, I would say the 3 is kind of an outsider. They're not completely isolated, but within this group that the 3 is going to be a part of, they will have a hard time fitting in, right? Like they'll only be friends with the 7 and not these other 2, but they'll be always kind of like hanging around anyway, all right? So I would say another thing that the graph tells me, just by looking at the graph, I can tell the one which is age 3, the age 3 kid will be sort of, I don't know, an outsider in that group, maybe. I'm trying to say this in a nice way, right? That 3 will be, able to relate to the 7, but probably not to the 12s. All right, that's the idea here. All right, so this is a very simple example where you can use a graph to get some kind of a feel for a situation in real life. All right, graphs are very good at modeling social relationships. Here we have kids which are connected based on their age, but I'm sure you can imagine like the correct mathematical way to think of a social network, like like an Instagram or something. The appropriate way to think about that mathematically is as a giant graph where you have a whole lot of people who are the vertices, and then those people have connections to one another based on like who their friends are in the social network. And the way to analyze social networks mathematically is always in terms of graphs. So it's super important these days. Be sure to follow me on Instagram. I recently made an Instagram. Nobody follows me. I'm not big on Instagram. All right, I got another example. So that was my first example of imagine a graph about some scenario. Here's another one. This is a little more, it's not more abstract, but it's a little harder to visualize. So here I'm going to say imagine a graph. I'll just tell you what the graph is and then we'll talk about it. A graph where each vertex is a Hollywood actor. And then I have to tell you, so this graph is huge. Like I'm not going to be able to draw the whole graph because there's thousands of different Hollywood actors. And I have to tell you what the edges are. 2 actors have an edge. If they appeared in the same film together. Right? This is the graph that I am inviting you to imagine. And this would be a typical homework or test question about, one of the things on the list said, imagine a graph. I will describe to you a graph like this, and then I'm going to ask you some questions about it. About, is it connected or not? What about the degrees of various things, and so on. All right? So this is what I'm asking you to imagine. Now, you can't draw this graph because it's way too big to draw, but I would say like a little piece of this graph. Maybe here we have, let's say, Chris Evans, the Captain America guy, right? And he's been in a lot of movies, so I would say there's like lots of edges coming out of here. And I don't know, there's too many to, what happened? My doc appeared. I think it'll go away. I don't know. Too many edges to draw them all in, but I could say like one of those edges goes to, I'm saying Scarlett Johansson, right? Because they were in those Marvel movies together. So there is an edge like that, right? There's many more edges, but that's one of them. And then Scarlett Johansson. Here, I'm going to put another one. Adam Driver. Remember that guy? He was in a movie with Scarlett Johansson where they like yelled at each other in a room. There was a meme about it. I never saw this movie, but they were in a movie together, right? But actually, I looked it up. I don't believe that Adam Driver and Chris Evans have ever been in a movie together. So there is an edge here, and of course many more edges, because these people have all been in many different movies. But there is no edge from Adam Driver to Chris Evans, because they were never in a movie together. At least I don't think so. I looked it up. All right. So this is a graph. All right, this is like a little piece of that graph. Really, you can't draw the whole graph. You have to just imagine it. So I will ask some questions here. In ordinary words, can you say, what does the degree represent here? Like, for instance, if I told you that Adam Driver's degree in this graph is, say, 47, what does that mean? His age? It's not, no, the graph has nothing to do with how old anybody is. 47 is, I think he's younger than that. I don't know, whatever. It's, yeah, what does it mean if I say the degree? Remember the degree means how many edges are in here? Anybody say? How many movies? It's something like that. It's not exactly how many movies they've been in. You got an idea? How many movies they've been in with other people. Something like that. This is still not exactly how I would say it. Anyone want to say a slight variation on that? It has to do with, you have to say something about other people, because all of the edges in this graph represent other people. Yeah?
How many times him and another actor appeared in the same film?
How many times? Something close to that. These are all very similar. I was going to say how many other people they have been in the same film with. All right? It's how many other actors there are that this guy has connections to. So when I say, for example, like if the degree of, Adam Driver is, say, 45, this means Adam Driver has been, I think probably in real life it's more than that, but if it was 45, then that means Adam Driver has been in movies with 45 other people. Right? Because the graph is about people and connections between the people. I heard a few times somebody said it's the number of movies they've been in with other people. That's not exactly true, because, for instance, they could have been, like Adam Driver was in 2 different movies with Daisy Ridley in the Star Wars movies, right? That doesn't count for twice, though. He has only one edge from Adam Driver to Daisy Ridley. So it's not about how many movies, it's about how many other people they have been in movies with. Sorry, it looks like my doc is not going to disappear. It's all right. All right, this is what the degree represents in this graph. Here's another question. This is maybe an easier question, perhaps. Who has a bigger degree? Let's say Tom Hanks versus Tom Green. Anybody know who Tom Green is? No. This is, do you know?
I think of John Green, like the science guy.
Yeah. Tom Green. He was like a weirdo actor in the 90s who was very briefly married to Drew Barrymore. He had a very strange talk show, which was a instant flop. Anyway, who has a bigger degree? Since you've never heard of Tom Green, this is a hint. I think the answer is Tom Hanks, because Tom Hanks was in more movies with other people than Tom Green. Tom Green was in a few movies. He wrote and directed his own film called Freddie Got Fingered, and it was a huge flop. Anyway, the answer is Tom Hanks, right? Because Tom Green, he has been in some movies, but he's by no means a big star. So Tom Hanks, the answer is Tom Hanks. He has a bigger degree because he's been in lots more movies with other people than Tom Green has. Been in lots more movies with other people than Tom Green has. All right, Tom Hanks's degree is probably in the thousands, I guess. I mean, he's been in tons of movies with lots of other actors. Okay, here's another question. How about, I happen to know Britney Spears was in only one movie. Anybody seen the Britney Spears movie? This was not a movie about Britney Spears. She was like an actress in a movie entitled Crossroads. I haven't seen it, but this is just for your information. What does that mean about the degree of Britney Spears?
Wouldn't we have to know how many people were like starring in the movie though?
Yes. Yeah. So the question, maybe a more specific question. Does that mean that Britney has degree 1 in the graph because she was only in one movie? And I think what you have interpreted is no, because the degree of Britney in the graph is how many other people she appeared in the movie with. So her degree is not 1, even though she was only in one movie. She will have several connections to the other stars of that movie, whoever they were. I don't know who they were. All right, so the answer is no. Her degree is, actually, you could be fairly specific about this. It's the number of other actors in that movie. All right, so it's not 1. It's fairly small, but it's not 1. Far less than Tom Hanks. All right. Okay, one last question about this, and then we gotta go. Is the graph connected? Is the graph connected? That means, remember what connected means? I mean, you could say it means the whole graph. If you looked at the whole graph, it'd be like one big chunk. But that's actually, that's very hard to think of it in those terms. Maybe the technical definition of connected is a little more useful. It means, given any two actors anywhere in the graph, can you always make a path from one to the other inside the graph? Now, among the portion that I drew right here, it is always possible, like to get from Adam Driver to Chris Evans, you can go through Scarlett Johansson, right? Is that actually always possible between any two actors? Like somewhere would be Tom Hanks. Do you think it's possible to find a bunch of movies that people were in together and eventually end up at Scarlett Johansson from Tom Hanks? I think probably that is possible, right? Even someone like Tom Green over here. He was in a few movies. Probably it is possible to connect him up with these other ones. So I'm going to say the answer to this is probably, this is harder to say for sure, mostly. Although, on the other hand, I could probably believe that there was maybe some guy who was in a movie like all by themselves and never in another movie with anybody else. I don't know. That might be, depends like what you're going to count as a real movie. Like I've made movies of myself to text to my friends or whatever, and I've never been. So if you include that in the graph, then I'm never going to be connected to Tom Hanks. But I will say probably mostly connected. This means, i.e., like what I mean by that when I say this is any one actor can join with any other actor through edges in the graph. This could be a fun sort of pop culture game to play with your friends. Can you give me a graph? Can you give me a path in the graph from Tom Hanks to Kevin Bacon? And then your job will be to name a bunch of movies that somebody was in. Actually, they were both in Apollo 13, so that's not very interesting, but you know what I'm talking about. All right, we'll do some more examples like this next time.